Okay, welcome back. So we're on section 11.3, which is called integrating factors. And basically what we've accomplished so far is figured out how to make total differential forms, test if there exists a primitive to a differential form, and then compute the primitive. But today we're going to see why that's useful for solving nonlinear differential equations. So let's start with a nonlinear differential equation, and this kind of harkens back to our very first theorem of this chapter, where we want something like y prime equals g of xy. We want that to actually be a ratio of partial f partial x and partial f partial y, and we can satisfy this particular condition where the right hand side is a ratio of a partial f and a partial f partial x and a partial f partial y by rearranging the original one, and we recover a differential form which looks like the following. Right, how would I do that? Maybe I should write that out for you. Write something like dy over dx equals g of xy. I multiply across by dx, and I get dy is g of xy dx. And I subtract dx to the left-hand side. I have something like, or I subtract dy to the right-hand side. I have something like g xy dx minus dy is 0. And looking at that, I can really quickly test whether or not this is an exact form or a closed form to see whether or not there exists a primitive, because my primitive would give me exactly this situation. Well, testing that, I recover that I would need that partial g partial y is negative partial 1 partial x, which is 0, which means that g of xy is actually only a function of x, which you can solve really easily because this is just y prime equals g of x, or rather that y is c plus an integral of g, because it doesn't depend on y at all. That's not going to be good enough for us, right? This is not even a nonlinear ODE anymore. It's now all of a sudden it's linear, so there must be something more clever going on. And I want to jump up a little bit and look here and mention that this could have been equal to partial f partial x over partial f partial y times mu of xy divided by mu of xy, and in rearranging something like this into a differential, I'm going to end up with a completely different differential than rearranging maybe my original one with g. And because of the cancellation that could occur when I take ratios of partial derivatives, because of the cancellation that might be able to occur, we run into a lot of really strange problems that we wish wouldn't be there, but unfortunately are there. And there was a reason why I used mu there, because that's actually where we're headed. So, if I were rearranging the version with two mu's, all of a sudden I would put a mu, right? So this is the version that I originally started with today. You can imagine I could multiply this entire expression by mu of xy. And in doing so, I recover the following expression, which I can then test for closed exactness. And under testing that for closed or exactness, I end up with the closed form criterion of the following. That my expression is going to be closed if and only if this is satisfied for some function mu, right? This is ugly. This is really not a very pretty expression. This is partial g partial y times mu plus a g of xy partial mu partial y is negative partial mu partial x. That is a terrible expression. But unfortunately, it's the one that we've got. So the integrating factor, which is my definition and also the title of this section, says the definition is I give myself an integrating factor, mu. Mu is called an integrating factor of the differential form g of xy dx minus dy. So there's a differential form. Mu is an integrating factor of that if it satisfies this equation. Now this is a partial differential equation. Now, something noticeably nice about this is that it's actually a linear partial differential equation. But it is a partial differential equation, and that's not the class that you all signed up for. So unfortunately, these integrating factors, you need to solve linear PDEs to be able to find them. But what we can do is be given them, right? So in the next example, I'm given, I start with an ODE, nonlinear, y squared over 2xy plus 1. And I claim that negative 2xy plus 1 is an integrating factor for the differential form, which would result. And we can test that by just plugging it into the differential equation. And what we get is that the left-hand side of my linear PDE is equal to the right-hand side of my linear PDE. I guess I forgot a negative sign there, but they are equal to each other. And that means that you have an integrating factor. Now, what does it actually mean to have an integrating factor? It means that the total differential form can actually be solved, or the ODE can be solved. So the main theorem of the integrating factor section says, given a nonlinear ODE, y prime one dimension, y prime equals g of xy, and its associated differential form, if I have an integrating factor, then I gain an implicit solution by computing, this comes from our previous section's theorem, right? By computing x, then the integral from 0 to 1, g of tx ty, mu of tx ty, minus y, integral mu of tx ty, and then equals c. So this gives you an implicit solution to the original ODE, y prime equals g of xy, given some integrating factor mu. Now the proof of that will be an exercise. It's not that hard. Given previous theorems, you just kind of put a lot of them together, but that is how we're going to solve most. Actually, this is the only way. This is the only way we know how to solve ODEs, is with these integrating factors, and the following. Now, a lot of times they look a little bit more simple than that. So, like for example, in this exercise, we can solve that, noting the integrating factor, because then we just use the theorem. We multiply, right? So we take g, which is this, we multiply by the integrating factor, which is that, and we get that g times the integrating factor is y squared. And so in the first term, we have ty squared that we integrate. In the second term, we just multiply the negative of the integrating factor. And so we integrate 2tx ty plus 1. And if I go ahead and compute this integral and simplify it, what I get is xy squared plus y. Okay, so if I actually compute all of that, xy squared plus y. Notice that integral was equal to c, so I'm saying that my implicit solution is given by xy squared plus y equals c. So the theorem basically told me how to find this implicit solution. I can go ahead and solve this for y, right? This is not the worst to solve for y. I've included a nice little remark here about inverting the quadratic, right? How would one actually solve this for y? You can read through that remark and make yourself believe that actually, given this expression in c, you can solve it for y, and you actually get this expression. Y is a function of x. Here's the solution to the original nonlinear ODE. And see, so it's not, these nonlinear ODEs, it's not very straightforward at all, right? Because if I jump up to the top, if I weren't given the integrating factor, I wouldn't know how to solve that nonlinear ODE. And even looking at the solution there at the very bottom, negative 1 plus or minus root 1 plus 4cx divided by 2x, and then I jump to the top, how does that solve y prime equals negative y squared over 2xy plus 1? It's kind of magic, right? But it does definitely give you a solution. You have to be given that integrating factor perhaps a priori, or maybe that's a really good excuse to go ahead and take a PDE's course, because it is a linear PDE. So there's my proposition, actually. We can get away with something even easier. This proposition says if the linear PDE, now in terms of some capital M, this is a different linear PDE than the one I had before with mu, so this is a capital M. So if this has a not, and it's a lot easier, more easily straightforward to write down. So it's just a derivative in M of x plus g derivative in M of y equals 0. If that has a non-trivial solution, meaning partial M partial x is non-zero, right? Because if partial M partial x were 0, partial M partial y. If partial M partial y were 0, then this whole term drops out and you could just let M be like a constant or something. And so you don't want something like that. But if that has a solution, you can actually compute an integrating factor by taking a partial derivative in y of capital M. And more importantly, you actually get an implicit solution right away. It turns out that this capital M was the original primitive function which solves my ODE y prime equals g of xy. So more or less, this proposition is saying another way of solving y prime equals g of xy is by solving the PDE, linear PDE, partial m partial x plus g of xy partial m partial y equals 0 for a non-trivial capital M, and then you recover your implicit solution. So that's really an interesting approach to this, and it's directly related to the integrating factor, because you can see in the proof, if you rearrange the integrating factor identity, go through a little bit of work with in fact your theorem 7.3.2, this is your linear Cauchy problem solution. You can actually solve the linear Cauchy problem solution. You end up with the equation that we have at hand, perhaps with an h on the right hand side, but in fact all of them with an h on the right hand side can equivalently have a 0 on the right hand side. So don't pay too much attention to that, except for maybe the bottom statement, which I've already circled. So if you want, you should freeze frame that right there. So the implicit solution to the ODE y prime equals g of xy is given by m of xy equals c, where m solves the top ODE right there, or PDE right there. So that's really what you want to think of with this proposition, but it's directly related to integrating factors. And that's why I included here. I have a very long remark about how nonlinear PDE, or nonlinear ODEs and linear PDEs are very closely related. They're like best friends of one another. And this is something we'll revisit in chapter 13 as well. But I'm not going to go through this here, so it's something maybe that you would enjoy reading about if you're very interested in PDEs. Okay, so finally then I have an example where I say, suppose that some function, suppose we were just handed the solution to this lovely PDE right here. And suppose that solution is x to the 3/2 y to that lovely PDE. I'm saying find the solution to the nonlinear ODE, y prime equals negative 3/2 y over x. And in fact, we could use the second part of the proposition to recognize that it's just, the implicit solution is just this equals c. But we could also use the first half of the proposition to say that the partial derivative in y of capital M is an integrating factor. And so we get x to the 3/2 as an integrating factor. So let's solve this with the integrating factor technique. We jump back to the integrating factor proposition, and we have to solve these integrals with some t's sitting around. And supposing we do, we get negative x to the 3/2 y equals c. Now, that should be fine, because if it's equal to c at the end of the day, then a negative c and a positive c are the same thing, which is why that was still true. And in fact, if I set this equal to c and I solve for y, I recover the following. That is the solution to my nonlinear ODE. Okay, so that's actually all I have for today. The next section will be kind of the most important one, but this one was a little bit of a nice direction to head in to see maybe where all of the motivation and the way that we construct solutions to nonlinear ODEs comes from. All right, see you in class. Bye.